Log on, tune in, find out. Another good idea from Cambridge.
Since I submitted the title of the talk, I have rethought the contents a little bit. So probably W-algebras will be on the background somewhere, but I will probably not mention them. But there will be a special series of talks by Ivan Losif on W-algebras, so he will tell you about that part of the story. So I will change the emphasis a little bit. And in fact, before I do the talk, I'll just try to do an overview of what I'm going to talk about. So basically, this by necessity will be very vague because this is an overview. So I just want to spend the first 5 minutes to sort of tell you what my plan is for these 3 talks. And in doing an overview, I will consider the most special of all cases, namely the case of the symmetric group. So for the purposes of this overview, F will be the ground field. Actually, for the purposes of the whole 3 talks, F will be the ground field. Let's assume that it's algebraically closed, just in case. And let's define its characteristic by P, which is arbitrary. Let's denote by SD the symmetric group on D letters. The first observation, which I think is actually new, is that, although meaningless the way I'm going to state it, is that the group algebra of the symmetric group has a non-trivial Z grading. Non-trivial, well-hidden Z gradient, which has to be defined, and I will define it. And therefore, we can, instead of considering usual representation theory of symmetric groups, we can consider graded representation theory of symmetric groups. So we can consider the category F as the not mod, but G mod of finite dimensional graded FSD modules. So this is the category of finite dimensional graded FSD modules. And the first thing which I want to promise is that in doing so, you're not losing any information. Namely, for example, if you're interested in irreducible modules and you don't care about graded irreducible modules, all irreducible modules are gradable. So you might as well consider all graded irreducible modules. But you actually do gain a lot of information if you do graded representation theory, because you can see gradings and the information which comes from that. But at least it has to be promised that no information will be lost. So this is really what I want to do. I want to do the graded representation theory. And a standard way of doing this, or one of the standard way of doing this these days, is to consider the big Grothendieck group, which is the Grothendieck group of all symmetric groups. So this will be a direct sum, by definition, over all D greater than or equal to 0 of the Grothendieck groups of FSD graded modules. When you consider the usual Grothendieck group, it's a free Z module on irreducible modules, but now it's actually a free Z QQ inverse module. So this is a free Z QQ inverse module. Where the action of Q corresponds to the grading shift. So if I want to multiply the class of a module M by Q, this is the same as, for example, by Q. Then this is the same as shift module M by 1 in the grading up. Okay, so there is this natural Q action. And then there are some well-known exact functors on these representation categories, which are refinements of induction and restriction functors, usually called Fi and Ei respectively. So there are exact functors between the two categories, f as d g mod and f as d plus 1 g mod. This way we can do EI, and this way we can do FI. And this is going to be for every I in I, which by definition is integers times 1 in the ground field F. And I will set up this notation much more carefully when the overview is over. And so these functors correspond to the linear operators on the Grothendieck group. And after extending scalars to Q of Q, this becomes now a vector space, infinite dimensional vector space with the same basis but over this field. So this becomes the basic module, what's called irreducible module with the highest weight lambda 0. This becomes the basic module over the quantum group, over the quantized enveloping algebra. UQG for an appropriate Kac-Moody algebra G. If characteristic is positive, then G is SLP hat C, a fine Kac-Moody algebra of type AP minus 1 upper 1. Or if characteristic is 0, then you can take SL infinity. And so from the modern point of view, you might say that this representation theory of symmetric group, or graded representation theory rather of the symmetric group, categorifies the basic module over this Kac-Moody algebra. And this connection is actually a deep connection. It's not only on the level of vector spaces, not only is it on the level of the Chevalier generators, although I forgot to mention that. So this identification of this Grothendieck group as an irreducible representation of this Kac-Moody, of this quantum Kac-Moody algebra, is so that EI and FI, you can see from the notation already, correspond to the action of the Chevalier generators. Of UQG. What else do we have on the side of representation theory? Well, we have blocks of the symmetric group, or the blocks decomposition. So here we have blocks, and the blocks will correspond exactly to the weight spaces on the side of the Lie theory. What else do we have? We have action of the affine Weil group, and on this side it corresponds to the derived equivalences constructed by Chuan-Cruquier. So here are Chuan-Cruquier equivalences. Correspond to the action of affine Weil group. I have to be a little bit careful here because I know that this is true at q equals 1, and usually this story is being done at q equals 1. So the new part here is the grading, and to tell you the truth, I haven't thought at all about if there is anything new to be said here about if you take gradings into account or not. But at least at q equals 1, this is a true statement. Branching rules, or modular branching rules, properly understood, correspond to the crystal graph. So you can really see that this connection is quite deep. Specht modules, or classes of Specht modules, correspond to the standard basis, what can be called. And maybe the most interesting part of all, the classes of simple modules, or the classes of irreducible modules, at least conjecturally, and at least in certain region, which I might call James region. In the James region, according to the James conjecture, in fact equivalent to the James conjecture more or less, correspond to the dual canonical basis. In the basic module. Okay, so this is sort of a general picture which I wanted to present in this overview, and I want to work towards this. Not quite literally, because I might not prove these things, maybe will not prove anything at all, but I will work towards that. And I might also work towards that more generally. For example, you can do it not only for the basic module, but for other modules, maybe for other Kac-Moody algebras and so on. So I'll give you some background which will help you to or maybe will help you to move forward with this. Okay, so that's roughly what I want to talk about. Okay, so now this is the end of this kind of BS part. Now let me try to start my talk again and try to do things more precisely. And I will start with something which I will refer to as the Lie theoretic notation. Actually, I probably shouldn't erase, but okay. So I start with something which I will call Lie theoretic notation. Well, I will start with some Lie theoretic notation, but the point is that at this stage it will really sound like a red herring, this Lie theoretic notation. It will sound like rather artificial or simply silly, because Lie theory, the information from Lie theory which I'm going to need here is going to be purely combinatorial, and it will look like this Lie theory is just artificially brought in, but in the end we will see that it's not, and that this is actually the right thing to do. Okay, but for now it will sound silly. And so again, just to start all over again properly, let's take F to be an algebraically closed field. Of characteristic P, but this P will play not such an important role actually. Instead, I will have another letter E, which will be reserved for something which I will call quantum characteristic, and that will play a role of characteristic. For example, F could be C, and I could work with the root of unity. E is primitive root of unity, in which case I want to think of E as a characteristic. So this characteristic is not going to be that important of this field, but the quantum characteristic is going to be important. Okay, so F is an algebraically closed field. Now, we discussed with Meinhof how we should coordinate our talks, and we discussed it only yesterday after he was done with one of his talks. And we thought that maybe there will be an overlap, but then we decided that there probably won't be a very big overlap, and if there will be an overlap, then we can at least guarantee that all the notation will be different. And so that will be good enough. So the first thing which I cannot do, I cannot use Q where he used it, because Q, as you have seen, is going to play a completely different role. Q is taken. So what should I call a parameter for the Hecke algebra? And I decided to call it Xi, I'm afraid. So Xi is an arbitrary invertible element, an arbitrary non-zero element of a field, and this is going to be a fixed parameter. And so you should think about it as this parameter Q in the Hecke algebra in Meinhof's talks. But also this parameter Xi could also be 1, which will sort of correspond to the degenerate situation where I work with symmetric groups. So I want to cover all bases in that respect. And corresponding to this parameter and to this field, which are always going to be fixed, I'm going to associate this quantum characteristic E, which is going to be the minimum of all numbers m, of all positive integers m, such that 1 plus xi squared plus dot 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 plus xi to the m minus 1 is equal to 0 if such number exists. And we will say that E is 0 if no such m exists. If no such m exists. So let's consider two special cases. If Xi is 1, then what's E? if my parameter is 1, then E is a well-known classical object. Which is called characteristic of the field. So if psi is 1, E is indeed a characteristic, so I do have right to call it characteristic of the field. And if psi is not 1, let's say psi is, well, let's say f is C, characteristic 0. And let's take psi to be e to the power 2 pi I over e. Well, if it's a primitive root of unity of degree e, then e, because you can multiply it with psi minus 1, and you'll just get psi to the m minus 1. So then e will be the order of this root of unity. And so this e I want to call quantum characteristic. It sort of plays the role of the characteristic of the ground field. OK, so to this e, I'm going to start associating some Lie theoretic data, which, like I said, at this stage will seem rather artificial. First, I want a vertex set, which is just going to be z mod ez. So it's all integers if e is 0, and it's integers modulo e if e is positive. By the way, the psi could be generic. You know, my field could be C of psi, or C of psi. So psi could be generic, in which case, of course, e is also e is also 0 because there is no such m. So this case is also covered. So I will consider this set, which I want to think of a vertex set of a Dynkin diagram of appropriate type. Before I do that, however, let me introduce for the future the number nu of I. And the number nu of I is going to be defined for any I in I, and it's going to be an element of the ground field F, and it's defined just to be I is if psi is 1. You see, I can interpret this element as an element of the ground field. You can easily see. Or it's going to be this if psi is not 1. And again, this makes sense because you can see even if it's root of unity, then it's an E root of unity, and then this is defined up to this. So these are well-defined numbers in F in all cases. Okay, so this is nu of I. And now I'm also going to consider the Lie type, or the quiver gamma, which is going to be A infinity if E is 0, and it is going to be of type A e minus 1 upper 1 if E is positive, or it's just a linear quiver, infinite linear quiver, A infinity. And in this case, it's a cyclic with E vertices. The vertices are naturally labeled by the set I. So here they are labeled by integers, 0, minus 1, 1, 2, minus 2, etc. And here are, again, 0, 1, 2, up to E minus 1. So I guess I identify numbers from 0 to E minus 1 with this residues modulo P. And we will need it much, much later, but since I am at it, I'd like to fix this too. It's not very crucial, but it will be convenient to actually fix orientation for this quiver. And I will always work with orientation of sort of going from smaller to bigger. Although here, the meaning of that is rather obscure. So this is a Lie theoretic data. To it, I can associate Cartan numbers, or Cartan matrix Aij, which would be 2 if I is equal to j, 0 if I is not connected to j in the quiver, for which I will use notation not connected in the Dynkin diagram. And then it's going to be minus 1 if I is connected this way or this way, just connected, I could say. And then because I did not exclude the case E equals 2, we could work in characteristic 2, for example, or at q equals minus 1. A sub 1 upper 1 is allowed, and therefore I could have this double edge. And by the way, I forgot to do this. In this case, orientation will look like this. So this is the case A1 upper 1. And so in this case, I will have minus 2 if I have double bond between I and j. OK, so to this data, as usual, for example, in Katz's book, you can associate the realization of a Cartan matrix. So you have roots and co-roots and all this stuff. I will tell you what I need from that. Again, just very rudimentary pieces of that picture for now. I don't even need H as such, but because realization according to Katz is a triple, H pi check. So let me say that this is a realization of the Cartan matrix of the appropriate type. In particular, we have simple roots alpha I labeled by the set I, and we have the fundamental dominant weights, which are sometimes called omega I or sometimes lambda I. So since I'm following Katz, I will use capital lambda I's. Again, for I in I, so these are the fundamental dominant weights. For the corresponding type. There is a normalized invariant form. On H and H star. And it's defined so that alpha I, alpha j is precisely aij, and lambda I on alpha j is precisely delta ij. And finally, just two more standard pieces of notation. I will use the dominant integral weights, denoted as usual by P plus. So P plus is the set of the dominant integral weights, which is sum of z greater than or equal to 0 lambda i's. And I also use Q plus, which by definition, again as usual, is a similar sum with alpha I. So non-negative linear combinations of simple roots, non-negative linear combinations of fundamental dominant weights. Okay, so this is the Lie theoretic notation, which is going to be valid throughout all lectures, and I hope it's okay. Now I want to talk about the objects properly, and the objects will include the symmetric group, but I want to work as promised in the generality of cyclotomic Hecke algebras, both degenerate and non-degenerate. And so in the degenerate case, you will get degenerate cyclotomic Hecke algebras, which include just symmetric group. So this will correspond to the case xi equals 1 and lambda being lambda 0. Okay? But it makes sense to do these things in general because they usually work in general without too much hassle. It's a slight lie, but normally if you can do something for symmetric group, you can do it to a large extent to this larger class. And we will discuss these dynamics in due course. So for now, I want to introduce the objects which I will work with. And I actually want to do it kind of a little bit slowly. So again, I want to remind you that throughout, f is fixed, unless I want to work with two fields, in which case I will tell you that this is one and this is the other. But throughout, f is fixed, and the parameter xi is fixed. So for example, if I define algebras, they are all going to be algebras over f. Okay, so this is part of the definition. And so the first thing which I'm going to do, I'm going to define the algebra HD by generators T1 through Td minus 1, and relations, the usual relations, Tr squared equals xi minus 1 Tr plus xi times 1, and Tr, and the cost relations. Tr Ts is Ts Tr if R and S are far apart. and tr plus 1 tr if they are not. So if xi is 1, then HD is the group algebra of the symmetric group. But if xi is not 1, then we get the Hecke algebra over the field F with parameter xi, just exactly as in Ismainov's talks. Okay, so otherwise HD is the Hecke algebra corresponding to the symmetric group of type A. Is the Hecke algebra of type AD minus 1 over the field F with parameter xi. Now, this algebra has a large commutative subalgebra generated by the so-called Eustace-Murphy elements. And the idea, which goes back at least to Okounkov and Vershik, but well beyond that, is that you can try to play with this commutative subalgebra as if it was a Cartan subalgebra, and you can try to play Lie theorist while working with the Hecke algebras. Let me talk a little bit about that. So let me denote by LR the rth Eustace-Murphy element. So LR, by definition, is going to be, now I have two cases, xi is 1 and xi is not 1, and so the definition is slightly different. I'm going to take 1r plus r minus 1r if xi is 1, and I'm going to define it to be xi to the 1 minus r, tr minus 1, dot t2, t1, t2, t1, t2, dot tr minus 1 if xi is not 1. And actually, the precise formulas are not that important, but I hope I didn't make any mistakes. So the main properties of these are that they commute. These are L1 through LD are the Eustace-Murphy elements, which I will abbreviate to JM elements. And their main property is that they commute, or their first main property is that they commute, for which there are long and short ways to check. And so they generate certain subalgebra, which is commutative subalgebra, whose structure is actually quite unpleasant, but apparently so is life in this situation. But at any rate, you can consider sort of the weight spaces of modules with respect to this commutative subalgebra. We have it 2 times. Yeah, I think this is the right definition. So we sort of go to the middle and then go back. So in particular, if R is 1, then L1 is an empty product, should be interpreted as 1 in the second line. And in the first line, it's an empty sum, should be interpreted as 0. So the first JM element is pretty silly, always, in all cases. Okay. There is, I know what you might be alluding to. There is another kind of closely related way to define these JM elements in such a way so that when you put xi to 1, you really get the degenerate JM element, in which case the eigenvalues of these elements will be different from the ones I want. So I sort of use this well-known renormalization, so to say, of the JM elements. I think this is correct. There are enough experts here who would tell me if this. Okay, so here's the first lemma, maybe. Let M be a finite dimensional, well-known, very well-known and very easy thing. Be a finite dimensional HD module, then all eigenvalues, you see eigenvalues in principle could be arbitrary elements of F, but they're not. They're sort of say integral, integral in our sense. So the all eigenvalues of these elements are of the form, all eigenvalues of these elements in this finite dimensional module are of the form nu of I for I and I. So they're not quite arbitrary, they're sort of as integral as you can hope for. So for example, if you work with symmetric group in characteristic 0, this would really mean integral. Okay, and so because of that, I can write down every, and because they commute, I can define weight spaces. So let's take any tuple I1 through ID in I to the D, and corresponding to this tuple, we can associate the corresponding weight space M sub I in any finite dimensional module, which is just simultaneous generalized eigenspace for these commuting elements with the corresponding eigenvalues. So it's a set of all V in M such that LR minus nu of IR to sufficiently large power kills V. So this is for sufficiently large n and R from 1 to D. Okay, so this is simultaneous generalized eigenspace with the corresponding eigenvalues. And we know that there aren't any other eigenvalues. Therefore, I can decompose M as a direct sum of weight spaces. And so in that sense, you can start asking various questions about modules. And one of the first questions which you usually ask is, what's the dimension of reducible modules, for example? But here you can ask more. You can say, what's the formal character? So what are the individual dimensions of these weight spaces? But as I want to explain, there is an even more refined question which really should be asked, and should be the question, what is the Q character? That is, you should grade the module, and you should consider graded dimensions of the weight spaces. And that seems to be the right degree of generality for now. Okay. Okay, so from this point of view, it's now natural to introduce affine Hecke algebras. So let me denote by HDAF, following Ian Grainovsky's notation, the affine Hecke algebra. So this will be the degenerate affine Hecke algebra. If psi is 1, and it's going to be the usual affine Hecke algebra corresponding to GLN if psi is not 1. And so let me try to motivate this. Of course, this object perhaps doesn't need to be motivated, but let me motivate it from the point of view of what we are going to do, and also define it. So let's consider first case psi equals 1. Okay, then I mentioned that we have these commuting elements inside of the group algebra, and because they commute, we can do weight spaces and so on. But it's rather hard to say, for example, which weight spaces occur. You know, it's not like for the usual Cartan algebra where you can do anything you want, and then induce and then consider Verma modules and so on and so forth. So here it's not quite clear what weight spaces can even happen ever, and it's because this algebra is pretty nasty. This commutative subalgebra, I don't think it's even known what it is by generators and relations or anything at all. So you don't really want this Cartan subalgebra. It's nicest of all things. You don't want it to be nasty. So what you want to do is you sort of want, okay, you can say, okay, it's nasty because we put into this prison of HD, but you want to take it outside and free it. And consider instead just, you would like it to be polynomial algebra so that you can say there is any weight. Okay? So what you do in order to go from this to this, you sort of just free it. Okay, so you sort of just take HD of to be, well, what you want is, you want to have HD, of course, but then you just want to have this polynomial algebra, which you just tack on. Okay, so I'll have this free generators x1, xd instead of L1, LD, which will generate a polynomial subalgebra. But it's not just going to be tensor product of this with that, because that would be silly. It should remember somehow something about HD. And what can we remember from HD? We can remember relations between t's and x's. Okay, x's could be free. There will be no relations between them except that they commute. But the relations between t's and x's still make sense. And those we just want to preserve. So what you have to do is you have to compute relations between Coxeter generators and the Murphy elements, which are explicitly defined. And if you do it for symmetric group, for example, you will very quickly find out that it's not going to be, well, you will fairly quickly find out that the interesting relations look like this. SR, LR is LR plus 1 SR, so it sort of tries to permute them, but then there will be an error term, which I think in this case will be -1. And just take these relations and you put them here, and that's how you can define this. Okay, so to be more precise, affine Hecke algebra, in this case, is going to be the degenerate affine Hecke algebra as defined by Drinfeld first, I think. It's going to be the algebra generated by these generators, and then usual relations. In this case, it's a 1, because we deal with the degenerate case where xi is 1. And then Coxeter relations for t's. So this will guarantee that these guys generate a copy of the group algebra of the symmetric group. And then x's commute. This will eventually guarantee that these x's just generate a copy of the polynomial ring. And then relations between t's and x's are taken from relations between Coxeter generators and the Murphy elements. And so TRXS is going to commute if S is not R and R plus 1. And then the only other relation which suffices is TR XR plus 1 is XR TR plus 1. And the next one actually follows from it, but I'll write it down anyway. -1, which comes exactly from this. So this, I hope, motivates well from the point of view of this representation theory, the introduction of the degenerate affine Hecke algebra if you work with the parameter xi equals to 1. And because of this definition, because of the way it is defined, there is, of course, surjective homomorphism from affine Hecke algebra onto the finite Hecke algebra, which sends Ti to Ti and XR to LR. So there is a natural homomorphism, HD of onto HD, which sends TR to TR, and which sends XR to LR, to LR for all admissible R's. And in fact, you can say a little bit more. You can say precisely what the kernel of this is. And the kernel of this is the ideal generated by the element x1. It's clear that x1 goes to 0 because I mentioned that L1 is 0. But it turns out that the kernel is precisely the two-sided ideal generated by x1. Okay, so this is the picture. You have HD, and any representation of HD via inflation is representation of affine Hecke algebra. But affine Hecke algebra sees more representations, and that's the game. Okay. Now, you can do all the same when xi is not 1. Do the same and everything goes through. and you know how to find the missing relations. And if you do the same, you'll get the usual affine Hecke algebra. So I guess I'll skip this case. Now I want to motivate the definition of cyclotomic Hecke algebras. So we thought that this was kind of natural, but now you see we decided that maybe it's nicer to study this representation theory because it sees more representations and because it has a nicer Cartan subalgebra without any nasty relations. But when you do this representation theory, you can say, okay, so if you want to understand, for example, this algebra, it's enough to consider just this integral eigenvalues for the x's. And it turns out that even if you're not only interested in that, it's still enough to consider only integral eigenvalues because you can reduce everything to this case. So you can consider the integral eigenvalues, but then you can say, well, how do we get this from that? Well, we get it by imposing a very strange condition that x1 has eigenvalue 0 only, because you just kill x1. So you can say that to go from here to there, what we do, we say we want x1 to act as 0. But then you can say, well, maybe I don't want x1 to act as 0. Maybe I want it to act as 5. Or maybe I want it to act as 5 with Jordan block of size 2. So maybe instead of this, I want to kill x1 minus 5 squared. Or maybe you just want to prescribe eigenvalues and the sizes of possible Jordan blocks. So in this case, you just take any polynomial with integral coefficients, say. It turns out that, again, you can reduce to this case. And you just put any polynomial on x1 here, and you can say, okay, I will impose a relation that x1 minus 1 to the power 100, x1 minus 7 to the power 200, and x1 minus 3 to the power 700 is 0. Okay, so you impose eigenvalues on possible Jordan blocks. If you do this, you'll get precisely the cyclotomic Hecke algebra. Okay, and so this is going to be my next move, but I'm going to record this information in a strange way. I'm going to this is where this silly combinatorial data coming from Lie theory begins to show up. So I want to fix a dominant highest weight. Remember that my f and my psi, they give me some some dominant weights, give me some Lie theory in a rather artificial way. So I want to pick lambda to be any dominant weight. Okay, what I really want to pick, I want to pick up a bunch of non-negative integers. But of course, they are going to be the coefficients of the lambda i's, so it's the same thing. And so then I will define hd lambda to be hd of. And now I'm going to kill this polynomial with integral eigenvalues. And then the sizes of the Jordan blocks will be controlled precisely by the components of this dominant weight with respect to the fundamental dominant weight corresponding to I. Okay, so the fundamental dominant weight is a nonlinear, is a non-negative integral combination. So this, again, is AI if lambda is a sum of AI's lambda i's. So these multiplicities, I want to read off these multiplicities of the roots just as this evaluation of the fundamental dominant weight on alpha I. This is non-negative integer, so this makes sense as a polynomial. And I will take two-sided ideal generated by this element. That's my cyclotomic Hecke algebra. And of course, from this point of view, you can see that HD, which we considered from the very beginning, just means that I take x1 minus nu of 0 once. So this is HD lambda 0. The zero's fundamental dominant weight. And it is in this sense that symmetric group or the usual Hecke algebra is a special case. It just corresponds to the special dominant highest weight. But there are all the others, and there are no reasons to exclude them. So this is the family of algebras I want to work with, and these are the cyclotomic Hecke algebras. Okay. So the next thing which I want to do is I want to show you a non-trivial presentation for these Hecke algebras. Of course, the way they are defined as a presentation. So this is a presentation of a affine Hecke algebra. You just throw in one more condition, that polynomial is equal to 0, and that's a presentation. But this presentation, again, is good for some things and is not so good for other things. For example, using this presentation, it's extremely hard to see the gradient which I want to see. And I claim that these algebras are, these algebras possess a well-hidden non-trivial gradient which amazingly can be spelled out very precisely. And you can sort of get your hands on it. The fact that these algebras have non-trivial interesting gradients has been conjectured, I think, by Rukia first and also by Will Turner. But they have not been constructed before. And definitely, I think it was somehow difficult to believe that they can be constructed so literally and so explicitly. So let me tell you, to convince you that this is actually rather explicit, I will have to sacrifice something, and I will probably not finish writing down the theorem which I wanted to write down. But I still want to tell you the generators, which will be the generators. So basically, what I want to do, I want a new presentation for this algebra by generators and relations, and these generators will happen to be homogeneous for the presentation, which will be manifestly clear from the relations. Relations will be homogeneous. Okay, and so I just want to tell you that there are no mysteries with this, or maybe there is just one family of these elements which are mysterious. So the first thing which I want to do is I want to define some idempotent. So for every I in I to the d, there is an idempotent, possibly 0. For me, 0 is allowed to be idempotent. I don't know if it's, is a 0 allowed to be called idempotent? Usually not. So, but for me, it will be. So there is an idempotent. In fact, it's not so easy to say when there's 0. There is an idempotent E of I such that, well, this is just a weight idempotent, such that when you take M and you multiply it by E of I, just get the ith weight space. This is what the idempotent does. And in fact, this is the only slightly unexplicit part of the story. So these idempotents are not a piece of cake to write because they are obtained from the Murphy elements LR by some sort of Lagrange interpolation polynomials. But this has been done by Murphy. So basically, you want to project onto weight space. You know how to write if you have elements and you have simultaneous decomposition to weight spaces, and then you work in polynomials and you want to write down the thing which will project you to the weight space. And because the action is not semi-simple, you have to take large enough powers, and you have to write down some sort of Lagrange interpolation polynomial which will do that. But the truth is, even though this is not completely explicit, we sort of don't care. We can make it as explicit as you want in many respects. So, and these are the only non-explicit guys, but they are quite nice. So they are orthogonal polynomials clearly, orthogonal idempotents clearly, and they sum to 1. All but finitely many of them are 0. So this is actually a finite sum. And so they are orthogonal. And so this bunch of idempotents is the first set of generators. Okay, so the second set of generators is essentially Murphy elements, but not quite, because I want to make these Murphy elements nilpotent. And normally they are not nilpotent. So what I want to do, I sort of want to subtract the eigenvalues individually on which weight space, then they will become nilpotent. And the clean way of doing this is to introduce the element YR instead of LR. And YR is nothing but LR minus IR, or nu of IR, on the corresponding weight space. And the clean way of doing this is just to say this is a sum over all I and I to the d of now my LRs are actually called XRs by now, because I'm in general cyclotomy Hecke algebra. So I'll just take XR minus nu of IR. So I take away the corresponding eigenvalue on the ith eigenspace. So this is a well-defined element, right? Because this, all but finitely many of those idempotents are 1. So just on each idempotent, I tell you what to subtract. And so these elements happen, these elements y1 through yd happen to be nilpotent. So what do I have so far? I have E of i's, and then I have y's. And these guys commute and these guys commute, because they are defined in terms of commuting elements and scalars. And then there is one last family of elements, which will remain a little bit mysterious for now. They sort of want to be shadows of Kochster generators, but they are not, and it's probably not the right way to think about them. The right way to think about them, if you are an expert, is they are sort of intertwiners. Intertwining elements in the sense of Rogowski and Chirednik and others. And the problem is that intertwiners are not really defined in the affine Hecke algebra, because in order to define them, you have to localize. But it turns out that in cyclotomy Hecke algebra, they are defined. But these guys are actually not the intertwiners, but they are appropriately rescaled intertwiners. And this rescaling is very important. But that's as much as I want to tell you about them. On the other hand, these most mysterious of all elements are defined completely explicitly by some explicit formulas. So in that sense, they are nice. But now I do have 7 minutes. So I want to state the first result, which we proved with John Brandon here this year. And you're not supposed to speak about these results proved less than 15 years ago on the instructional workshop. But I think this is actually quite a basic thing. It's just symmetric group if you want. So I probably should be allowed. So and it's just another presentation. And let me assume for purely instructional purposes that E is not 2, because in this case relations are. In this case, I just have to write a little bit more. But this case is covered, but I will not cover it for pedagogical reasons. So HD lambda is generated by the element star subject to the following relations. Subject only to the following relations. For all admissible R and I and so on. And I'll just write down those relations if you allow me. You see, when you see a new presentation, you have to stare at it for a week usually before you can tell something whether you like it or not. And we don't have this week, but still I'll write this down. I don't think it will be totally useless. Okay, so what it says is that first of all, what I already told you, that EI, EJ are the idempotents, which are orthogonal to each other and summing to 1. But I do not insist that they are all non-zero. In fact, it will follow from relations in a non-trivial way that some of them are 0 and some of them are not. And this is not a trivial issue. Then Y's commute with E's and with each other. Yes, some of them are 0, some of them are. I'm sorry, I forgot E of I. E of I, E of j is delta ij, E of I, which covers the case that it's an idempotent and that they are orthogonal. So Y's commute with E's and with themselves. Now I have to tell you how Y's and Psi's commute, and that is going to depend on idempotent. You see, if you know how to commute over the idempotent, or times the idempotent, then you know how to commute, because then sum of all idempotents is 1. But on each idempotent, they commute a little bit differently. And this is where Lie theory begins to come in quite an amazing way. And it's a Lie type, this, not Lie type AD minus 1 of the symmetric group, of the Kochster group. It's a different Lie type. It's this Lie type, which is going to come into these relations. So, for example, if you want to commute Ys with psi r, well, it's psi r Ys if S is not R and R plus 1. It's to be expected, perhaps. But then if you want to commute psi r and yr plus 1 times the idempotent, then you're going to have two cases. It's either going to be yr psi r, E of I, if IR is not IR plus 1. And it's going to be YR psi r psi plus 1 E of I if IR is equal to IR plus 1. So in this case, it looks a little bit like the relation in affine Hecke algebra, in degenerate affine Hecke algebra. And then there is a similar relation for psi r YR, except that you just have to change 1 plus 1 to minus 1 again as an affine Hecke algebra. So I told you how to commute psi's and y's. And the last thing is to commute psi's. Okay, well, again, they're trying to be sort of satisfying Coxeter relations. For example, psi r psi s is psi s psi r if r and s are far apart. But the Coxeter relation has an error term, psi r plus 1 psi r minus psi r plus 1 psi r plus 1. And this error term, again, depends on which idempotent you are on. And so almost always this error term is 0. But there are cases when it's not. And in which case this is 1 or minus 1. And it depends. So it's 1 times E of I under the following circumstances. If we have IR and then IR plus 1 and then IR plus 2 as follows. IR plus 2 should be IR, and it should be connected by arrow to IR plus 1. So it's kind of this IJI case where I and j are neighbors in the Dynkin diagram. It's minus 1. Excuse me? Say it again.
So, not connected, but
connected. Arrow should go from R to R plus 1, and R plus 2 should also be equal. Okay? And then it's minus 1 if they are connected in the opposite direction. IR plus 2 is equal to IR, connected this way to IR plus 1. And it is honest 0 in all other cases. So it's almost a Coxeter relation, but sometimes there is an error term depending on the idempotent, actually. Finally, there is a quadratic relation, psi r squared. And that might be the most interesting of all, but and so this is what quadratic relation looks like. Psi r squared on the idempotent is 0 if IR is equal to IR plus 1. It is 1, or rather E of I, if they are not connected. And it is YR plus 1 minus YR if they are connected in one direction, and minus that if they are connected in the opposite direction. YR minus YR plus 1. Okay. Finally, there is a cyclotomic relation. Remember, this should depend on the dominant weight lambda. If I left it like this, it would be the version of a fine algebra, and I will comment more on that. But I want a cyclotomic algebra, so I also want to throw in the cyclotomic relation, which in this case looks like, again, we are trying to kill y1, but for y1, remember, it's nilpotent, so only one eigenvalue is allowed. Now, eigenvalues are taken care of by the idempotents, rather, not by the true eigenvalues. So the relation is y1 to the power lambda alpha I1 on the idempotent I1 is the first component, is 0. It tells you the sizes of y1, of the nilpotent Jordan block of y1 on each weight space for the Hecke algebra. Okay, so I don't have time to tell you all funny consequences of that, but I'm sure that we missed a bunch of consequences actually too. But I'll tell you a couple. So here's one really funny thing. Where's Xi? It's a rhetorical question. How come Xi does not show up? Because remember, my Hecke algebra depends on the parameter Xi, Q in Meinhof stock. Why there is no q? How could that be? Is that a mistake somewhere? This algebra clearly depends on psi, right? We know that okay, there are some cases when the group algebra of the Coxeter group is isomorphic to the Hecke algebra, but there are some cases when it's not. And so how could the relations for the algebra defined for any parameter q not involve q in them? If you look carefully, and I promise you there are no xi's in these formulas, even if you ignore the formulas. Okay, well, so psi plays a role, but in a very indirect way, in a very funny way. Psi determines the Lie type, right? Because remember that this Lie type was determined depending on E, and E depends on psi. Okay, so psi is in, but it's hidden. So this is one funny situation, which does have some curious consequences, which I will have to mention next time. And just the other thing which I want to mention and write down today is the following corollary. That this algebra is graded. We can prescribe degrees to the generators, and you will see that all relations are manifestly homogeneous with respect to this grading. So this grading is actually very easy. So corollary 1, which I want to mention today, and I will write down the rest next time. There is a unique Z grading on H d lambda. Such that degree of the idempotent is, of course, 0. We don't have to worry which of them are zeros or not, but degrees of all idempotents have to be 0. Degrees of y's are 2. You know, it's as silly as it can get. And then on psi's, it's a little bit delicate because it depends on which idempotent you're on. Psi is actually not homogeneous, but psi r e i's are homogeneous. And this degree is, well, it's given by the Cartan number. It's 0 if IR is not connected to IR plus 1. And it's 1 if IR is connected to IR plus 1 like this, and it's 2 if IR is connected by double bond. So I guess this is nothing but minus AIJ. Oh, I'm sorry, minus AIR IR plus 1 Cartan integer. That's what the grading is, prescribed explicitly. And I guess my only exercise and actually request is to check that with respect to these gradings, these relations are homogeneous, just to make sure I didn't screw anything up. Okay, so that's it for today.